philosophical point of view, the most relevant scientific result of the last 30 or 40 years is the creation of far from equilibrium thermodynamics by several people, including Ilya Prigogine, who obviously won a Nobel Prize for his work on his. Why is that important? Because, well, first of all, thermodynamics is very important for philosophy, for a process philosophy, because thermodynamics deals with quantities like temperature, pressure, in which differences in temperature, differences in pressure drive flows, drive processes. They are like fuel of potential energy that's embodied in the difference itself. As long as the difference doesn't get cancelled, it can drive a process. So from a philosopher's point of view, particularly a philosopher like Gilles Deleuze, who is a process realist, that is, who believes that reality exists independently of our minds, but that we need to explain every single item in that reality via the process of production that brought it into being. Intensive differences in temperature, differences in speed, differences in density, and so on, are crucial, not only because they are differences, but because they are productive. Now, when thermodynamics started in the 19th century, basically as a result of studying the steam engine. The steam engine had already appeared among the population of machines as a new species of machine, and the person, the craftsman who created the first one was quite ignorant of science, so that this was more of a product of craftsmanship rather than applied science. When scientists approached the steam engine, they approached it as an animal, as a new species of machine that had already appeared among them. So that's a very interesting fact, because it's not like astronomy that has ancient beginnings. This was a science that began with industrialization. The first branch of thermodynamics, or the first version of thermodynamics in the 19th century, was called equilibrium thermodynamics, and studied only the final equilibrium state, that is, the state that things have after the differences in intensity have been cancelled. Therefore, equilibrium thermodynamics could not conceive or did not have a way of conceptualizing differences in intensity as philosophical entities. Then, somewhere in the first few decades of the 20th century, came the second version of thermodynamics called near equilibrium thermodynamics, in which systems were departed a little bit from equilibrium, and then they were allowed to reach equilibrium again, but the intensive differences were very, very low. It was already progress, because we were already studying the approach to equilibrium. We were not studying systems that had already reached equilibrium, but the intensive differences were so small that they did not reveal any further phenomena. What Prigogine and workers and scientists like him who work in far from equilibrium thermodynamics do is they create laboratory setups in such a way that they do not allow the differences in intensity to cancel themselves. The laboratory setups are open, in the sense that they are flows of matter or flows of energy constantly coming from the outside, refreshing the system. And the whole idea is to study the system, to study what happens in a system if you do not let the differences in intensity be cancelled. This is what is philosophically crucial about it, because it is the study of the differences themselves. And so while in equilibrium thermodynamics, even non-linear systems exhibit the simplest form of behavior, for instance, steady-state attractors or steady-state stable states, far from equilibrium, you discover that there are not only steady-state equilibrium states, but also periodic equilibria or limit cycles, and chaotic attractors or quasi-periodic fractal forms of stability. In other words, even the most non-linear system studied near equilibrium does not reveal the full repertoire of self-organization. You need to push a non-linear system far from equilibrium, and it's only in that region of intensity that the full repertoire of virtual attractors becomes revealed. So philosophically, that is very important, because as a philosopher, you want to study the ontological status of attractors, for instance, you're looking at equilibrium systems, then you're going to be disappointed because equilibrium systems hide the virtual. Equilibrium systems do not allow the full expression of all the potentialities of virtuality. If you study systems far from equilibrium, opens a window into the virtual in the sense that the full repertoire of attractors now becomes part of the dynamics of the system. In addition to revealing the potential of nonlinearity, far from equilibrium thermodynamics, it reveals a matter as capable of self-organization. It is in a way the two sides of the same question. Now the other branch of science that can benefit the most from this is evolutionary biology. Evolutionary biology, when it only considers genes, enzymes, proteins, and so on, and natural selection, leaves all kinds of holes in the story, which can be taken advantage of by creationists and intelligent design people to pretend that they're finding holes in Darwin's theory. Most of those holes can be plugged, as Stuart Kauffman and other biologists have shown, by incorporating far from equilibrium thermodynamics into evolutionary theory, because then the matter that genes act on is an active matter, is a morphogenetic matter, so that all that genes have to do is guide this active, morphogenetically pregnant matter in different directions to produce different species, and you don't have to count on genes to do everything, which is one of the reasons why there's holes in the theory of evolution. Well, I mean, the only philosophy that can benefit from science is materialist philosophy. If you're a phenomenologist who believes that the only thing that exists is phenomena, that is, things as they appear to us, and you're talking simply about our phenomenal field, you cannot benefit from science at all. Therefore, when Heidegger makes silly remarks like science doesn't think, you can expect that from phenomenologists. They simply cannot benefit from science. Materialist philosophy, on the other hand, can benefit from science, but only as long as it's non-equilibrium, non-linear science, because equilibrium science and linear science show you a side of matter that is too impoverished, too mechanistic in the old-fashioned sense. Non-equilibrium or far from equilibrium, non-linear systems display so much more variety of behaviors that then, as a materialist, your notion of matter, your concept of matter becomes different, becomes an active matter, a matter that's capable of morphogenesis, and therefore it reveals a creative world that does not need humans to be creative, but was creative 6 million years ago before we came into existence, and will be creative even if we blow ourselves out of existence. There are two types of artists, right? The artists that go for phenomenology, they're not going to shake anything because they are just dealing with concepts, with words, extremely long explanations of the works of art that are completely beside the point. But I hope that there will be one day a new generation of scientists that recovers the respect for matter instead of just linguistic concepts, that begins dealing with pigments again, that begins dealing with sonic matter, that begins dealing with the body as a material system in choreography, and that this re-enchantment of the world that far from equilibrium thermodynamics together with nonlinear dynamics have revealed to us becomes a source of inspiration for these artists, so that they help people understand that the world does not need a god to tell it, be creative, have form, that the world itself is artistic in the sense that it's in itself capable of generating form, and therefore art then will become not a form that the artist cerebrally imposes on an inert matter, but a partnership with matter in which form comes from the interaction between the human and the non-human.